are going to start, once you send that to me, we are going to start with problem number, or example number 2. Yes, sir.
Whenever I try to output that, it declares software.
When you try to upload it to send it to me?
Yeah, it closes the app.
Okay, well, open it up and then you can select what pages you want to send and it won't close you out. Did you hear it, Sophie?
I mean, it is.
They want to listen, they can listen. Okay.
No.
I'm going to start on this in like 30 seconds, so make sure you're with me in 30 seconds.
Do you have wire cutters? I don't have one. It keeps snagging.
Super random. I don't think I have wire cutters, but I bet you Miss Weber would.
Tell her in the middle school today. I'm just joking.
Okay. Sorry.
Yep.
Now that's on record for anybody that listens to this video. Oh. Yeah. There's a coat that Molly's not allowed to wear because it has like this Velcro that will snag anything. So it's ruined several shirts of mine. So we just banned that coat. Alright. We're going to do example 2, example 4, and example 5. Example 2 has to do with something going into an object. In this case, it's going to be a conical paper cup. Those are like the paper cups that would be like a little water station that are like a cone, or what you would get a snow cone in, or something like that. So this is a pretty common problem where something's flowing into an object. Sometimes it's a tank, so it's rectangular. Sometimes it might be a bowl, so it's spherical. In this case, it's going to be a cone. And then it might be leaving at another rate, which we'll get into. But in this case, we are drinking root beer from a paper cup that's in the shape of a cone. The cup has a diameter 8 centimeters and depth 10 centimeters. Hi. Does it have to be right now, or can it be at the end of the hour? Is that alright? Okay. I'll talk to you really quick.
She's sitting there.
Oh, you know. Sit on it.
I don't want to go to
Okay, I see what you did there. Okay.
Hey, you did that?
What?
Your face. Funny.
Yeah, you did. Oh, that's tiny, man.
I'll make you sit on one of those little notes and then you can use them.
What? So let's bring both of them.
Huh?
Let's bring both of them.
Yeah, can you dip in this truck?
Yeah. No, I don't let her.
Okay, so I'm just going to start writing. I know that was an interruption, but... Okay. So what object are we looking at again?
A cone.
Everybody, what object are we looking at? A cone.
Root beer.
You have root beer flowing in, and then it's just filling up. Maybe. No. You're making it leave the cup. So it's already in the cup, and then it's leaving because you're drinking it. At what rate is the level of the liquid changing when the liquid is 6 centimeters deep? At the instant the last drop leaves the cup. What's going on? I hope you've noticed, but like when you start to have questions, like they give you the scenario and then the questions, that's like your specific information is in those questions. So usually what you know is in the couple of sentences before. You know it's a cone. You know the cone itself, or the cup, has a diameter 8 centimeters and 10 depth. And then the root beer is leaving the cup at a rate of 7 centimeters cubed per second. So what did I say yesterday about something that's being cubed? As volume. So that's the rate that's given to us. So I know that dV over dt is going to be 7. Now, since it's leaving the cup, is the volume decreasing or increasing? Decreasing, so we should make that a -7. Okay. And what we want to find is the level that the liquid's changing at, or the rate the level of liquid is changing. So if you think of the level, that's the height. We could label that as dy over dt, but since it's talking about like the height or the level of the liquid, we're going to label it dH over dt. It doesn't really matter as long as you know what that variable is referring to, and it's referring to the level. So dH over dt. And the instant we would be looking at, the first instant would be when H equals 6. Good. So when it's 6 centimeters deep, so when H equals 6, that's the first instant. And then we'll talk about that last question. When the last drop leaves the cup, what's going on? The height is 0. Okay. All right. So the next, that'd be the first step. What was our second step in these? Draw. So I'm going to draw a cone. Try to draw it as best you can 3D. Now the actual paper, not the root beer inside, because the root beer level and volume is changing, but is the actual cup shrinking or increasing in size? No. So that I can label with constants. It tells me that the cup itself has a diameter of 8, and it has a height of 10. Right? Yes. And then I'm going to draw a little wavy line here to indicate where the root beer might be. But is that level changing constantly? Yep. So we're going to label those with variables. Now, I haven't given you the formula yet that we need to use, but actually in our formula we don't need the whole diameter, we just need the radius. So I'm going to label that with R. And then this would be what variable that we've indicated? That's volume. That's the level, so it'd be H, the height. And that's constantly changing, your root beer. Okay, so our third step here, what's our third step? Find the equation. Now, yesterday we talked about the fact that whenever your rate is volume, and we know it's volume because it's centimeters cubed, that kind of indicates to you what equation you're supposed to use. So we want to use the volume equation for what kind of object? A cone. So I forgot to scan that in yesterday, but okay. So we are looking at this scenario here. We have a right circular cone, and I will say this type of volume equation would be given to you either at the very beginning of the test, like the AP test, or I would give it to you in the context of the problem. That's not something that you're expected to memorize. Something like a rectangle, or length times width, or circle, like that stuff you should know by now. But this would be given to you. So we're going to write volume equals pi r squared h divided by 3. And now we have a problem that's presented. So I'm just going to talk through this scenario a little bit, because what's usually the step after this? Derivative. Now, if I was to take the derivative of this, derivative of v would be dv over dt. That's okay, because I have a dv over dt I can plug in eventually. But what's going on with the r squared and the h here? They're being multiplied, which means I would have to use the what? Product rule. And then I'd have a dh over dt and a dr over dt when I took derivative. But the only thing I'm looking for is dh over dt. There's no picture here to rewrite. So, write yourself a little note so when you're looking back at this later, you remember why you do this. We have to rewrite R in terms of H because I'm not given a dr over dt. Because I'm not given a dr over dt, I can't keep r in the equation when I take the derivative. I got to replace it with something. Okay. With your picture, everybody, all right? Okay. I'm going to take our picture and turn it on its side. And there's a reason for this because it'll be a little bit easier to see what's going on here. Since in my equation I don't use the diameter, I just use the radius, I'm only going to use half of this diameter. So what's the radius of this cone? 4. Now, if I was to make a shape here that I can deal with, I have a triangle that shows up there in my picture. I also have another triangle that shows up there. One triangle represents, this is like where the root beer is, and the bigger triangle is the actual cup. What are those two triangles called? Similar. Very good. Which means similar triangles can have different lengths, but what's true about all their angles? They're the same. Which is nice because then we can create some proportions with our sides because they're similar. So one length can be compared to the same type of length in the other triangle, and that ratio is the same for every side. So we're going to use that similar triangle scenario that we have, and I will say the reason I'm doing this problem is because the cone problems, whenever the cone pops up as a shape that you're supposed to use in related rates, not always, but often you have to do this similar triangle stuff. This similar triangle stuff doesn't really pop up anywhere else, just with cones. So you really don't have to worry about doing it until you come across the cone one. I'm going to set up proportions then. I want to rewrite R in terms of H. So let's start with the 4 because that compares with the R in my smaller triangle. So we can say that 4 is to R as 10 is to what? Because this 10 is this length here in my bigger triangle, is to H. Good. And then with a proportion, anytime you have a proportion, now we can cross multiply. So we get 4H equals 10R. And do I want to divide by 10 or do I want to divide by 4? What do I want to get by itself? Because I want to replace something. What do I want to replace? I want to replace the R. So don't I want the R? Don't I want to get the R by itself then? Yeah, so I can actually replace it. So I'm going to divide by 10, and so R is going to be 2/5 H. Now, this is a little side work you had to do, but you had to do it. Otherwise, when you took the derivative, you wouldn't be able to get to your answer because you don't have any R values, you don't have any dr over dt. So then I'm going to take my 2/5 H, and before I take the derivative, replace. It's okay with you, I'm going to move that 3 just right there. So now we replace R with what R is equal to, 2/5 H. And now taking the derivative is going to be a lot nicer because can't I distribute this square through to everything? So technically we're going to have an H squared, and then we're going to have an H squared times H, which is H cubed. Notice I haven't even taken the derivative, I'm just trying to simplify so I can actually take the derivative and make it work. So when I square the 2, I get 4 pi, And then we have 5 squared is 25. 25 times 3 is 75. H cubed. So all I did is square the 2, square the 5, and then just combine my two fractions together. Alright, now I can take the derivative. And when I take the derivative of v is dv over dt. Because remember, with related rates, we're taking the derivative with respect to time. And then when I take the derivative of h cubed, bring the 3 out front. So we get 12 pi over 75. H squared. And what do I have to include there? dh over dt. Good. Okay, and then in step 5, I should be able to plug stuff in for everything that's there except for what I want to find. And what do I want to find again? dh over dt. So if you look back at what we labeled in step number 1, we want to find dh over dt when h is 6. So I can plug 6 in for h here. And then I know dv over dt is negative 7. So then the only other variable that would be left is what I want to find. So we're okay there. And let me just put this like on a side note. If you were to take the derivative and you get to step 4 and you're fine, and then you get to step 5 and you try to plug stuff in and you're missing a lot of information, that's probably because you had to do something similar to what we did here. So it is possible to get to step 4, but then you might have to back up and replace something. Alright, so I'm going to put in negative 7 for dv over dt. We have 12 pi over 75 times 6 squared dh over dt. And so in the calculator, you're going to divide negative 7 by a whole mess of things there. 12 pi, whoops, over 75. Whoops. I think I need parentheses. And then times 36. You should end up getting a negative 0.387. Now, does it make sense that my rate would be negative for dh? Yeah, because the height would be decreasing if the volume's decreasing. And the height isn't going to decrease at the same rate necessarily. What are the units on this? Centimeters per second. So that seems like a pretty logical answer, that would work for our height. Okay. Now, the other instant that we had to look at here was when h is 0. That's the instant the last drop leaves the cup. If I was to plug in 0 here, what happens? Makes everything cancel out. So if this comes up where stuff completely cancels with a rate, what that means is you're not able to find how fast it's going when that last drop leaves the cup. It's going infinitely fast. It's like taking 7 and dividing it by 0. And like that would be a scenario in algebra when we had a vertical line. And what do we say about the slope of a vertical line? It's undefined because it's infinitely, like there's no run, it's always infinitely rising. So when that happens with a rate, you just say it's going infinitely fast. You can't measure it to decimal. So that might be good to say here. And there's not really a way to show that because when you actually try to figure out algebraically, everything goes away. So you just have to know when that happens that you say it's going infinitely fast. Okay. going to do another one with similar triangles, not right now, but I want to do one more today so you get another look at it. So go ahead and switch to example 4 when you're ready. Yep.
What are these ones called?
Which one?
The volume and the flag ones. What are these ones called?
For example 4? These ones, since they have to do with angles, these ones we're going to actually end up using SOHCAHTOA for. All right, so we're going to find the rate of change in the angle of elevation of a camera 2,000 feet away from the base of a rocket pad at 10 seconds after liftoff. Okay, so do they give me any kind of rate in there? How do I know they don't give me any kind of rate? Because they asked me to find it. And usually if they give me a rate, what do I see? Something over something, like centimeters per second or inches per minute or something to indicate that it's a rate of change. One thing that would be given to you in this scenario, since they don't give you since I don't give you a rate, the position function would be something, they would have to give you some piece of information here. All right, I want to find, well, let's say what we know, which we might not know much right now, but we can probably figure something out. There's not a rate that I can write down, but I do know what I want to find. I want to find the rate of change in the angle of elevation. How do we usually label my angles? With what kind of variable? Theta or x. In this case, we're going to use theta because we're going to be able to draw a right triangle with this situation, so we'd want to use theta since we're in a triangle scenario. We want to find d theta over dt when what? When theta equals 10 or time equals 10. So we want to find d theta over dt when time equals 10. Now for the no part, I know that the position is this, but I could say that I know what ds over dt is. What is ds over dt? If this is function s, and ds over dt is the derivative of function s, can I take the derivative of that? 100t. So I could say I know that ds over dt is 100t.
Is it only 100 or 100T?
100t. Yeah. Okay. So the equation. Now this is going to be something. Well, sorry, we got to draw a picture first. We have a rocket. Oh, the reason I pulled this out is because I had a student like. Does anybody know who Byron Sweet is? Yeah, he drew pictures for all my related rates questions, and this one's probably one of his better ones. So I pull it out usually for these questions. So there's my there's my picture. It's much better than the rocket I would draw and the person I would draw. But you're 2,000 feet away from the launch pad. S is the height because it's the position of the rocket. It's a stump. It's a tree trunk. And then theta is the angle in the camera. So this is the guy with the camera. So if you want to at least draw the triangle to start with. Okay. And again, this is not 5. This is S because they gave me the position equation. That means the rocket's changing position all the time, so we had to label that with a variable. All right, now normally when we've had a right triangle, what did we end up using for our equation? Pythagorean theorem. But with the Pythagorean theorem, you have to have all 3 sides. Do I have all 3 sides? No. And a Pythagorean theorem doesn't have any kind of theta in it. So this is another type of equation that we have to include at the very beginning when we're making our general list here at the bottom. When theta is involved, a lot of times you have to use sine, cosine, or tangent, depending on what kind of stuff is present. And so if you want to write SOHCAHTOA, and then maybe do a little note that you use SOHCAHTOA when there's theta. So when you want to find d theta over dt, or when you want to, or when you know d theta over dt, that's when you would use SOHCAHTOA. All right. And then going back to this one, for SOHCAHTOA, I have the adjacent side to the theta, and I have the opposite side to the theta labeled. So what function has the opposite and adjacent side attached to it? TOA, tangent. So we're going to say, okay, tangent of theta is going to equal S over 2000. And then I'm going to take the derivative. What is the derivative of tangent? Secant squared. So we can say, okay, secant squared theta. Since I took something that's not a t, took the derivative of something that's not a t, I have to include d theta over dt. And then S over 2000, you could see this as 1 over 2000 times S. So what's the derivative of that? 1 over 2000. And then I'd have to include ds over dt. Now, I'm not really going to simplify any further because I'm going to see if I have to go find more information, but maybe I have enough to plug in. I have d theta over dt, or no, sorry, that's what I want to find. I have ds over dt, technically, because I could put it in 100t, but then I want to find it for when t is 10. So I have all the information there to plug in for that. What is the variable I'm still missing? Theta. So I need to know theta at the instant they want me to look at, which is when t equals 10. So I'm going to do a couple of things here with this original formula. Because remember, when we're missing information, go back to your original equation and then plug in to find your missing variable. Kind of like when you're missing your y, when you're finding the derivative, you have to go back and plug in your x to find your y to plug in. So, same type of thing. We're going to go here. Instead of s, since s is 50t squared, I'm going to write in 50t squared. Because I'm looking for when t is 10, so I can't really plug 10 in for s. But I can plug it into what s stands for. And so if I plug 10 in there, since that's the instant I'm looking for, I'd have, I'm running out of room here, tan of theta. Okay? Okay. Plug in, well, what's 100 times 5 or 50? Because that's what we would be doing here. 5,000. So 5,000 divided by 2,000 is 5 over 2. If you reduce everything. Okay. And then going back to trig a little bit, when I want to solve for theta at a certain instant, I use the inverse tangent function here. So you take the inverse tangent of 5/2, which we can do just on our calculator. So, I should probably check. Yeah, I'm in radian mode. So when t is 10, theta has to be 1.19. So I'm going to include that here. When t is 10, theta is 1.19. And then I can go back and plug everything in. So we have secant squared of 1.19. d theta over dt is what I'm trying to find. And then ds over dt here, I can plug in 100t, but what's the t I'm looking at? The time. So I'm just going to plug in 10. So what is ds over dt for this scenario? What's 100 times 10? 1,000. Everybody agree it's 1,000?
Yeah.
Yeah. Okay. And then it's just going to be taking, well, this is technically going to be 1/2 because things are going to reduce. But taking 1/2 and dividing it by what secant squared of 1.19 is. So secant squared can be a little tricky to plug in. So I'm going to do it here for you. 1/2, so 0.5, divided by secant squared. Now, secant's the reciprocal of cosine. So to plug it in, you have to do 1 divided by cosine of 1.19 squared. I didn't mean to do that. I have to have another parentheses here. Cosine of 1.19 squared. So you end up getting 0.069. So d theta over dt is going to be 0.069. Now, this is the angle of the camera. Does it make sense that the angle would be positive rate? Because the rocket's shooting up, so the angle would be getting bigger. After 10 seconds, with a rocket that's shooting up in the air, after 10 seconds, is it going to be pretty high up in the air? Probably. And so is the angle of the camera going to have to change very much? No. So we're going to give the units radians per second. I know that they didn't really tell you what the units were, but we're in radian mode here. We're not in degree mode. So you could use degrees here, and it would work out the same. And then you just label it degrees per second. Either way you do it. All right. I think I'm going to keep this for Monday. This is a shadow problem. There are shadow problems in the A1 practice. I think there's only one I gave you that's like this. So if you come across that one, just keep it for Monday, and I'll let you finish that one before you turn in the rest of them. Okay. So we're done for today. The notes.